Right, okay. So, I'm reliably informed that this is as far as we got last time, more or less. Yeah. So we'll just skip over the virtual Earth theorem again, because it's quite an important theory. It's actually quite straightforward, and it makes life incredibly easy for analysing more complicated circuits. So it's a really good thing to get your head around. So it says the result we got is exact, and it means this result here, which is the gain of the op-amp system, yeah, with feedback resistors around it. So this was the accurate version, and it got an A in it, and we said that A is really, really large in an ideal world, so this tends towards 0, so this tends towards R2 over R1, which in itself is a simple solution. So the gain of our amplifier was reduced to the ratio of two resistors, and we didn't care what the amplifier was, as long as its gain was very, very high. So that's the important point there. So we can look at an amplifier circuit, and we don't care who the manufacturer of the op-amp is. We can just say the gain is going to be R2 over R1 for an inverting amplifier configuration. All we've got to do is recognize it as an inverting amplifier. Okay. Oops. So that result is exact with the A in it. Reasonably exact if you approximate the A to be very large. The higher A is, the more exact it is. And in 99% of cases, it's exact enough that we can't measure the difference, which is pretty good. Okay. But we can get to that result, the final result, the approximated result, without the A in it, much more easily by applying this thing called the virtual Earth theorem. And we said there that if the circuit is working properly as a negative feedback amplifier, then to a very good degree of approximation, we can say that V plus minus V minus is approximately equal to naught. So the difference of the voltage of the input pins is very close to 0. And we did some work last time where we actually worked out, got an equation for the value of V plus minus V naught in this amplifier configuration. And we worked out that even for all kinds of signals going in, it's going to be a few microvolts, which first of all says we're allowed to use our linear theory because we're in the linear range of operation of the op-amp. And also it means that a few microvolts is pretty close to 0. So this is sort of stating that in those terms. Okay. So you can go back and look at the input transfer characteristic of the op-amp circuit, or the open loop op-amp. And this has to be less than a few microvolts. And we said it couldn't be bigger than about 100 microvolts if it was working properly anyway. Okay, so you don't have to worry about that too much. You can just say, I'll accept this is working as a linear amplifier, and therefore the difference between the two input terminals must be close to 0. That's what I mean. The difference between these two terminals is close to 0. Yep. And in this case, our inverting amplifier circuit, one of the inputs is connected to ground, so it's at 0 volts, because it's physically connected to it. And by the virtual Earth theorem then, this point must be at the same potential as this point. This one's at 0, therefore this one must also be at 0, or very close to it. And then we can apply our theory. It's not connected to it, there's no physical connection, because the input impedance is very, very high. There's a huge, great resistor between these two. But because there's no current flowing through, they are at the same potential. Yeah? So they're not physically connected. That's the best way to think about this. They're at the same potential. And as I think I mentioned at the end of the last lecture, what that means is that the op-amp, what it's actually doing is adjusting its output to maintain the difference of these 2 points as being 0. If the input voltage changes, and so this voltage looks like it's going to change, this will adjust its output to rebalance everything so it's 0. So it's balancing everything at the 0 point, or balancing it to this point, which in this case happens to be 0. Okay? So that's all the op-amp can do. Adjust its output, one way or the other, to maintain 0 at that point. And that's negative feedback. It's adapting itself to maintain this 0. Positive feedback is the other way. It looks at the difference here and says there's a difference. It adjusts its output the wrong way and makes the difference worse. That's positive feedback. That's not, you can't use your linear theory for those, but we'll worry about that later. So that's called a virtual earth. It's called a virtual earth because usually, but not always, usually this point is connected to what we would term earth, 0. This could be 10 volts, 20 volts, 30 volts, in which case this point will be 10, 20, 30 volts. Just because it's called a virtual earth does not mean that it is at 0 potential. Okay, that's a common mistake people make. Right, so assuming at that point then that V minus equals 0 because V plus equals 0, and we've applied the virtual earth theorem, we can say that the input current is just V in minus 0, because of that Ohm's law applied to that resistor, I in equals V in over R1, and therefore that also must mean that I in flows around the outside because there's no input current going into the op amp, so it can only go around the outside. This ends at 0. We can now calculate what the voltage at this end ought to be to allow those conditions to apply. Ohm's law again. So we can just equate those two equations to each other because they're both equal to I in. I in equals V in over R1 equals minus V naught over R2. And if you rearrange that and get rid of the I in, because you don't need that anymore, you work out that V naught over V in is equal to minus R2 over R1. Yeah, so we've effectively almost separated that part of the circuit from that part of the circuit because there's a 0 in the middle. Right. Got that? Just remember that the current through here is equal to the current through there, and everything else follows. Right. So that was the inverting amplifier. We might want a non-inverting amplifier. One where when you put a signal that's going up into it, you get a signal that's going up, coming out of it. Everything's in phase. A non-inverting amplifier. All right, okay. Another reason why we want a non-inverting amplifier is to do with input impedances, which you'll have looked at in the transistor lab, and you'll have realized that having a finite input impedance leads to loading effects. You can adjust the gain of your amplifier by knobbling its input circuit with a resistor. Okay, so if we look at the input impedance of our non-inverting op amp, you might think it's very high because I said the input impedance of the op amp was very high. The input impedance looking into here is very high, close to infinite in an ideal world. Okay? But the input impedance of this whole system, the whole lot, is not that. The input impedance of this is actually R1. As the signal comes in, it comes in here, a V in, goes through the resistor, and it sees 0 volts. Because the op amp is adjusting this to make it maintain 0. So actually, it's, as far as the signal is concerned, it's going straight into the ground, as far as you can see. So that makes the input impedance of this circuit R1, which is not infinite. Okay? So we've lost this feature of our ideal op amp, that it has an infinite input impedance. And we've replaced it with an input impedance that's actually equal to R1, which is not infinite. Which means that we can have loading effects if we're not careful. So the non-inverting amplifier is a way of keeping the simple gain control of just two resistors and relating their things, but also adding the high input impedance to the circuit as a whole. Okay? And so what we effectively do is we just feed the input, V in, into the positive terminal, and we connect what is currently V in to ground. Swap those connections over. Right? So it looks like this. Not drawn very well. That's a crossover. They're not joined. Okay? That makes no sense if they're joined. I haven't drawn it very well. So now, the input signal is coming straight into the positive input, which we know has a very, very high input impedance. And this other one, where the input originally came in, is now grounded. So now we've got this configuration to worry about. And I propose to you that this is a non-inverting amplifier. And we shall show it. So, let's apply the virtual earth theorem to this circuit. So the virtual earth theorem says there is no difference in the voltage between these 2 points. Okay? So what we effectively do is we work out an expression for V minus, we work out an expression for V plus, and we equate them to each other because they're the same potential. So if we look at V minus here, V minus is just the output of this potential divider between R1 and R2 driven by V out. V minus is R1 over R1 plus R2 multiplied by V out. And you can get that by just looking at it. Who can't get it by looking at it? Okay, so we can all see that's a potential divider. Good. Potential divider there. So, now we need to get an expression for V plus. V plus is V in. And that's it. V plus equals V in. And now we apply our virtual earth theorem and we say V plus equals V minus. So we can make this equal this. Okay. And if we do that, which is done here, okay, V in equals R1 over R1 plus R2 V out. We rearrange that to get V out over V in. V out over V in, the gain, is equal to R1 plus R2 over R1. It's a little bit different from the last one. And you can simplify that if you want, or put it into a more standard form, which is 1 plus R2 over R1. So it's not quite as straightforward as just R2 over R1 now. It's 1 plus R2 over R1. And what we should notice about this expression is always bigger than 1. So the non-inverting amplifier always gives you a gain bigger than 1. Okay. Well, you might always want a gain bigger than 1 as far as you're concerned. The other one, which didn't have the 1 in, R2 over R1, you can arrange R2 over R1 to be less than 1 if you wanted to, which means you can make an attenuator. You can make something that makes an input signal smaller, should you wish. A big signal, or make it smaller. You can do that. Can't do that with the non-inverting amplifier. But for most amplifying problems, that's not an issue. Bigger than 1 is fine, but there's a little bit of algebra to do to work out the absolute gain. Okay? If you make R2 equal to R1, for example, then the gain becomes 2. But see how easily we got to that by applying this virtual earth theorem here. This mysterious circuit, well, a bit mysterious. We haven't seen it before anyway, in this form. We've analysed it almost in our heads by just understanding this virtual earth business. Yes? Powerful technique, do you think? You wait till we get capacitors and inductors and resistors in these spaces. You'll be really pleased you've got it there. Right, so the non-inverting amplifier has advantages. Very high input impedance, because the input current is close to 0, because that's the nature of the op amp. And has non-inverting amplification. So what you get in is a replica, or what you get out is a replica of what you put in, just adjusted in its amplification. There's no phase inversions going on. So we might want to know what the exact solution is, in case it has to apply at some point. So, not assuming the virtual earth theorem, so i.e. not assuming that the gain A is super high, just that there's a gain A, yeah. So we're trying to work out where our limits may lie in this respect then, because we know the gain of the op amp falls away with frequency. So we can just look at this and go, again, V minus equals V out times R1 over R1 plus 32, that's times, it's not a convolution or anything like that. And we've still got V plus equals V in by looking at it, so that's fine. And what we need to do now is get a link between V minus and V plus. Now before, we said there's an approximation where we can assume they're the same. But if we're not allowed to make that approximation, then we have to look a little bit further, and we know that V out is defined by the op amp equation of A, V plus minus V minus. There's that output there, okay? And that's what the op-amp does. That's what it does. And it's all about this being high that we can make all these other assumptions. But if we can't make those assumptions, then we have to use this. If we use this, we can now substitute V plus for this, and V minus for that, and then we have to work it all through to see what we've got in terms of V out over V in, because then we've got V out, V in, and V out, and we have to just manipulate it a bit. So what I've done there, as it says, is I've taken the equivalent of V plus, which is V in there, and I've taken the equivalent of V minus, which is R1 over R1 plus R2, V out, stuck them in the equation, expanded it, and then if you expand that out with a little bit of effort, and this is where people can go wrong, you can go down all kinds of rabbit holes doing expansions and everything here. You're aiming for this kind of thing with an A on the bottom. Because when you've got that A on the bottom, when you're allowed to assume that A is large, then that will tend to 0, and the answer that you're familiar with drops out. So it's worth just running through these derivations occasionally, because you can end up, you know roughly what you're supposed to be doing. You do expansions, you do brackets, you do all kinds of stuff, and you end up with something that's a nightmare. And I've seen in exams people who have done 4 or 5 pages of going around in circles with expansions and not ever getting to this. They waste their time, they waste my time. So, it's easy if you know what you're aiming for. It's also easy if you've actually written it down on a bit of paper and tried it out. Yeah. What we might call revision. Targeted revision. Okay, so that tends towards R1 plus R2 over R1, which is 1 over 1 plus R2 over R1, as A tends towards infinity. Right, so in an exam, read the question. If it says you can make assumptions, then it's probable that you can assume the virtual Earth theorem applies. But you have to state it. I am using the virtual Earth theorem because, and give me a reason why it applies. If it says you can't make any assumptions, or you can't use the virtual Earth theorem, you have to do it this way. And it might not say, approximate it when A is large. It might just say, what's the answer? The answer is this. Because you're not allowed to make any assumptions about A. If the next part of the question then says, if A is large, what difference does that make? Then you can go to this bit. Yeah? So, read the question, answer the question. Don't just regurgitate the slides and hope that's good enough. That shows lack of understanding. Is that clear?
Yes.
Is the question?
What would be the reason for assuming?
Sorry?
What would be the reason for assuming the virtual Earth theorem? You have to just.
Because the reason for assuming it is that A is large. That you can allow A to be large. In a normal op-amp, A is large up until a high frequency when A is no longer large. Have you done the op-amp lab yet? So you've seen that the frequency response tails away. So if you're applying this at high frequencies, then A may not be large because the frequency response has dropped away.
Yes.
Under normal conditions, you may well you can assume that A is large if you're assuming that the op-amp is going to be operating in its linear region, should we say, which is most cases for linear amplifiers. Yeah. It's only if you're going up to high frequencies that you've got to start looking at your assumptions, because then it might not work as you anticipate. If you want an amplifier with a gain of 10 to operate across the audio band from 50 hertz to 20 kilohertz or something, then it's entirely legitimate to assume that A is large across that band for your operation. If you went up to 100 kilohertz with that same circuit, A would not be large at 100 kilohertz. So the response of your amplifier would change with frequency. What we would do is we'd make A frequency dependent. So you'd redo this calculation lots and lots of times with different frequencies, and you will find that it goes flat, 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 and then falls away, like you did in the lab. Yeah. So what you're saying is, as long as I can assume that frequency is not having an issue on my gain system, I can apply the virtual Earth and everything is hunky-dory. If frequency is an issue for me, then I need to consider what happens at high frequencies, and are my assumptions still valid? Most of the time they will be, but it's important that you find out if they are or not, because it means that you're using the wrong op-amp if it becomes important at the frequencies you're interested in. Is that clear? So it's going a long way ahead. We do touch upon this later. Right, so the general non-inverting amplifier. So we can extend this analysis to a general case. We can replace each resistor, R1 and R2, with a general impedance. You just call it Z. Okay? So Z can be anything linear. Okay? And then we can just replace Z or R with Z in our analysis. So thus, V in equals Z1 over Z1 plus Z2, because it still applies. V out over V in is this with Z's in it. So we've just replaced the letter R with the letter Z. Not much, but actually very powerful as we go forward. So you've got this general form. And this is when you can start to add in other stuff other than resistors into these things and apply those equations. Right, but we'll go for the simple special case first of all, the unity gain buffer. If we take the special case where Z2 equals 0, so we've got a short circuit round the op amp, everything's being fed back, yeah, and Z1 is infinite, yeah. Z1 would be connected from here to ground, but it's infinite, so open circuit there. We end up with this. Okay, so V out over V in, if we apply our equation here, becomes 1 over 1 plus 0 over infinity, which I propose tends to 1, because that's what happens in the real world. So now we've got a gain of 1. V out over V in equals 1, which is no gain at all. Yeah? So what goes in is the same as what comes out. There's no difference between it. So you might argue, why can't I just replace this with a piece of wire then? That'll be much cheaper and easier. Well, because this has certain features associated with it that is interesting. First of all, the input impedance of this is very, very high or infinite in an ideal world, because it goes straight into the plus terminal. And the output impedance of an op amp is actually very, very low, as you'd have measured from the labs. So what you've got something is that it doesn't care what the impedances presented at either end to it are. You don't get any loading effects. This acts as a buffer. It isolates two different parts of the circuit and takes away all the loading effects because of the infinite input impedance and the very low output impedance looking in. So it's a really, really, really useful circuit when you've got something really complicated. Might not be behaving quite as you think because loading effects, which vary with frequency, remember, are causing all kinds of grief. Separate your circuits with one of these, chances are the problem will go away. This is a really, really, really useful circuit. Really, really, really useful. Right. So we can analyze this with the virtual earth theorem, and it becomes incredibly trivial. V in equals V plus equals V minus, because that's the virtual earth theorem, which if you follow it round is equal to V out. V out equals V in. Doesn't get any easier than that, does it? Or does it? You don't know. You're hoping it does. Right, so high input impedance because it's going straight into the positive terminal, really good. Low output impedance of the op amp, which is really, really good. So extremely useful when connecting a high impedance source to a low impedance circuit or network. Takes away all these issues of loading. If you don't know what loading is, check back through the notes, make sure you understand it. It's very important. We've done labs on it, we've done notes on it. It's there. Right, using the same principles, we can create circuits that carry out basic arithmetic functions, such as addition or subtraction. And these are just developments of these inverting and non-inverting amplifiers. Consider the circuit shown below, and you'll have seen this in the lab, maybe done some preparation on it. It's an adding circuit, and it's going to add, in some shape or form, these two voltages to each other. Okay. It's going to make use of the virtual earth So we've got one here. And so we know that all the currents coming from here are going to go around the outside. But we've got multiple inputs, so working out what's going on here might be a bit more tricky. Yeah, we look at that. So we say, well, how can we make this a bit easier? We can understand things that have got one input and one output. Things with two inputs and one output. We're not happy about that. Well, let's use superposition. Let's suppress one of the inputs. Because it's a linear circuit. And then we've only got a circuit with one input and one output. We can worry about that because it looks just like, if we take away one of these, the inverting amplifier, which we know how to analyse. And then we just unsuppress this one, suppress that one, get the same thing with different numbers, add them together. That's the sort of general approach. When you start looking at these op-amp circuits and you haven't seen them before, you go, right, is there a virtual earth first? Can I justify a virtual earth? If the answer is yes, then suddenly all the linear circuit theory applies, and you can do nodal analysis, you can do superposition, you can do mesh analysis if you want to. And if you want to do it formally, you would then replace this with the model of the op-amp, which remember is two wires dangling and a dependent voltage source at the output, and you can do formal nodal analysis on it if you want to. So we've got a virtual earth. Okay. And we've effectively got Kirchhoff's current law here. All the currents add up and give us their output current, and nothing goes in here because it's an op-amp. So with the combination of that, a little bit of basic knowledge, and the virtual earth theorem, we can say generally that for this type of circuit, I out, current that comes out of this thing, is equal to the currents going in, added up, Kirchhoff's law. So I out equals I1 plus I2. And if you want to add up lots of things, all the way up to IN, we can extend this down further if you want to. And that I out is going to equal minus V out over RF, whatever V out is, because this is always going to be zero because of the virtual earth. So we know that the voltage difference across here has to be V out or minus V out. And I1 equals V1 over R1, again, because one ends at V1 and one ends at 0. So that's easy enough. And then so we can get expressions for I out, got one here. We can get expressions for I1 and I2. And, I1 plus I2 is going to equal I out. That's going to give us some kind of equation that gets us there. So we can write then, V out over RF, that's the total current, is equal to the sum of the individual currents, which was minus V1 over R1, minus V2 over R2 all the way along. And then we can rearrange that in, for two input system, very trivially, we end up with V out is equal to some modifier of V1 plus some modifier of V2 with a minus sign in front of it. You might argue that's subtraction, you'd be wrong. Okay. This is addition, because it's adding, followed by an inversion. That's not the same as subtraction. Put numbers in there and prove it to yourself if you want to. So this is a bit complicated. We've got lots of variables in here to play with. Well, say variables, constants in terms of the resistors. So we look to try and simplify this. One of the obvious things to do with complicated systems with resistors in is to say, well, what happens if I make all the resistors the same? That's a good starting point. So if I make all the resistors the same, in this case, so that becomes R over R, R over R, so they become 1, put it all in there. V out is equal to V1 plus V2, the addition, inverted. So we can put another inverter on the output to get our addition back if we wanted to, if we're worried about the minus sign. But that's what we've done. So we've got V1 plus V2 as our output voltage. So we've made an adder. And it also gives us a clue that maybe we can scale the weighting of the different inputs if we mess around with these resistors if we wanted to. We're not going to do that. We'd like a straightforward adder, please. So we just make all the resistors the same. So we've gone from quite a complicated op-amp circuit now to being able to analyze it in, well, a couple of lines of algebra. It's not even GCSE standard algebra. I hope you'll agree. So there's no excuse for getting this wrong in an exam, is there? Anyone got an excuse for getting it wrong in the exam? Right, you're all going to pass then, aren't you? Oh, you got one. Dyslexia, does that apply to numbers? Dyscalculia, that's numbers. If you've got that, then you've got a problem. I don't know. So, I'm not going to make light of it. If you've got dyslexia, then obviously you've got extra time and coloured filters and things you can apply. And you know, it's a problem. I know. So yeah, okay. So no facetious answers there. If you've got dyslexia, could be a problem, but it's a problem I'm sure that you're aware of and are able to cope with. I would hope at this point, if you've got this far. That's all I can say on that. You have my sympathy. Okay, so but the basic principles are easy. It's the concept and the vision that sits above this that's the hard thing. Yeah, the abstraction and the imagination that goes into saying, "Oh, how do I do this?" The actual implementation and turning the handle on the numbers is easy. Right. That's something else. Right. What we don't have is the high impedance of the non-inverting amplifier. So the input impedance is relatively low. So with our newly formed knowledge, if we wanted to put this into a system where loading might be a problem, any ideas what we could do? Yeah? A unity gain buffer. Yeah? If you're worried that whatever's coming in here has an impedance that might affect the values of resistors and therefore affect the accuracy of your adding circuit, then you just put unity gain buffers on the input here, and that isolates everything. And that gets rid of the problem of having a low input impedance here, because you've got rid of that with the buffer. Okay? That answer your question? Yeah? Happy? Yeah. Right. How are we doing? Okay. Subtraction. Difference amplifier. It starts to get a bit more interesting. So we're going to combine aspects of inverting and non-inverting amplifiers to make a true subtractor, rather than an adder with a minus sign in front of it. Okay. So we start with this configuration. And this is a bit trickier to analyze, but the same principles apply. Okay, we've still got virtual earth in the middle. Everything else goes with it. So we just need to try and work out what's going on here. So the usual starting point for op amps, it's a bit tricky, is just work out what's going on here, work out what's going on here, make them equal to each other, and see what drops out. Okay? So in this case, we look at it and we go, yeah, right, okay, R4 over R2 plus R4 gives us V plus and multiplied by V2. That's that little potential divider there. Tells us what V plus is. That's easy enough. To get V minus, it's a little bit more complicated. We start to do a bit of superposition on that. So we suppress one end, make that 0, look at the potential divider we've got. So this is the same analysis as we did for the inverting amplifier. We get one value there. We then suppress V out, unsuppress V1, work out what's going on. We've got those two there, and we can add them together. So V minus is given to us by this expression, which is messy, to say the least. And V plus is given to us by this expression, which is a bit neater, but it's still not straightforward. And then we can use the basic op amp equation again. V out equals A, V plus minus V minus. And we know what V plus is, and we know what V minus is, and we can throw that into the mix. And you end up with this, which looks very messy, or impressive, depending on your viewpoint. Right, so it's clear as mud. It should be pretty clear. Yeah, it might not be clear that this is a subtractor, but that's the basic system that we've got. Now we need to constrain it a bit with the value of resistors and stuff like that. Okay, so there's various different ways of doing this. Here's one example. We can multiply through. What I'm really trying to do is collect terms. So I'm trying to collect V outs on one side and V ins on the other side. You can do that however you like. I've stepped it through here because I tend to make mistakes. Over many years, mistakes have been ironed out of this. So we go. or show you working. I always think, I'm showing my working to you, you can show your working to me. Seem fair? In the exam? Then I can give you marks, even if you've gone wrong. Don't show me you working, and you go wrong, I can't give you marks. Makes things very binary. Okay, and then you can start to simplify things if you wanted to. I divided by A in this case, it says, and R1. To simplify things as we go down the train, and we end up with V outs on this side, and V2s and V1s on this side. Now you can start to see that there is a true minus sign here, V2 minus V1. There's a lot of the stuff in front of it, and it's not quite as straightforward as V out equals that. But, look, we've got an A on the bottom. A on the bottom is a good thing. So we will strive now to get rid of the A, or make A very, very large. Okay. So if we do that, yeah, this tends towards 0, we're left with V out. V out is equal to V2 minus V1, with a whole bunch of R's. 2 voltages subtracted. We've made a subtractor. Scaling may be all over the place, but we'll solve these problems as we come to them. So what we'll do now is go, okay, is there a relationship between those values of resistance that we can work with to make life easier for us? So we start by just saying, let's make all the resistors the same. See what happens then. All right, well, we'll do that in a minute. You can use the virtual earth theorem to do it as well, which gets rid of the A in the first place, so we've instantly assumed that A is large. If we assume the virtual earth system can apply, and it all follows through. It's easier. It's easier with the virtual earth theorem if you can make it apply. You get the same answer. So here we are, V2 minus V1, whatever. Okay. Right, so we've got this way of controlling the subtraction function using 4 resistors, R1, R2, R3, R4, make them all equal to each other. What do we get? Well, we get this with all the R's. You can see all the R's are going to cancel out, and we end up with V2 minus V1. So we've made a true subtractor. And one thing that we've done throughout this lecture is we haven't cared about what's in the op amp at all. There's a whole bunch of transistors in that op amp doing God knows what, and we don't care about it as long as we can say that A is very large and apply the virtual earth theorem. We've done adders and subtractors, we've done them in half an hour, and it's straightforward if you do a bit of practice. Same applies to all kinds of other circuitry with op amps. You just have to concentrate on implementing the function that you want in a clever way, and the op amp will do the rest for you. Right, so those are linear circuits. Virtual earth theorem applies. Everything is nice and linear. We can apply mesh, we can apply nodal, we can apply superposition, which we've done today. So we've seen examples of that. And hopefully you can see that applying this superposition and some of this Kirchhoff's current law stuff, which is effectively nodal analysis, is actually very straightforward. Yeah. So what we're going to do next is we're going to look at nonlinear circuits. And that says if we make the transfer function amplitude dependent, we have a nonlinear circuit. But basically we're going to use diodes and things. So more complicated functions perhaps, compression, expansion functions in mobile voice comms. Maybe Rob's talked a bit about that, I don't know. We're not going to go into the detail of that, but this is where it all leads in the end. And what happens is that we start to put nonlinear elements in the feedback loop. Okay, so we had resistors there before. Now we've got a diode. We can call it Z1. And then we can maybe start to apply the template work. But it's going to be a little bit more complicated than that. So we have to worry about what's going on. So I think it's a good place to probably stop. Some of you can reflect upon how you might start to analyze that with a diode in the feedback loop and what possible use it might be to us. And I'll fill in the gaps next time. Okay?
about the adder. I built this circuit and simulated. I found that if I don't have a op amp, the signal still some of
Well, it will still sort of some, but you won't get any gain. You won't get any amplification, and you won't get any, and you've got all kinds of loading effects. If you put something on, yeah, well, what you haven't done is all you've done is you've looked at two voltages on the oscilloscope, which has a very high input impedance anyway. If you then use that signal in some other circuit without a buffer or anything else, it's just going to go. But if you put a buffer in there, you've made an adder.
So op amp is just make it work correctly.
Yeah, it does things with the input and output impedance. It's very important. But if you put a buffer amplifier, you take that connection there of your sum point, put it into a buffer, draw the circuit, you'll get that adder circuit.
So if I don't use op amp like adder, I just use the buffer.
Yeah, well, the buffer is an op amp, and what you've done by adding these two other resistors to the buffer is you've made an adder.
Yeah.
More or less. Very simple adder.
And so, what is mean of the transistor matching?
And two transistors opposite each other, they have to be identical. Same size, same shape, everything else. If they're different at all, they're not matched.
Okay.
Yeah. And in a silicon chip, they can be made to be very, very accurate to each other. If you make this whole op-amp circuit on a circuit board with transistors, they'll all be different. And so the performance will be very, very bad if you use transistors as little transistors. You have to integrate them onto a chip and make them all identical.
I got it. And about this model, how can I get
That's a current source.
yeah, how do I get it?
You wait until the second year, and then someone else tells you how to make a current source.
Okay, okay.
Alright, okay.
Could you go back to the previous slides a little bit? No, just sorry, just do this. Oh, yeah. So why is a minus sign over here?
Why is the minus sign?
Why is V out equals minus V1 plus V2?
Because the configuration we've used is an inverting amplifier configuration.
But this is a. I thought this is a non-inverting amplifier.
No, that's inverting because it's coming to the negative pin.
Ah, so the input is going through the negative one.
Well, to balance this, to keep this zero, if this one goes up, this one has to go down.
Oh,
To make the zero in between. If this one goes up and this one goes up, you can't have zero in the middle.
so this place
That's always at zero.
Ah,
So if this
because
one goes up and this one goes down, because of the virtual ground here.
yeah.
Yeah, so that's an inverting configuration. So you get a minus sign.
What about the non-inverting one?
Well, the non-inverting one goes into the other terminal, so you go straight in here to the plus.
So if this goes up, this goes up.
Yeah.
Oh yeah. Okay. Thank you.
Thank you. So I'm not too sure. When you know that part when you said whether I can tell this is a voltage divider or not, I can't really see it.
All right, so they've got a resistor and a resistor connected to each other.
Yeah.
Can I draw on this?
The 100. Sorry.
So what you've got,
You're going.
so you've got a resistor and a resistor. This end is at V out. This end is at 0. And this is the minus point that you're interested in, so that's a potential divider.
Yeah.
Yeah. So if that's 1k and that's 1k and this is 5 volts and that's 0, this point here will be at 2.5 volts because it's halfway between the two. So
Okay.
it's just divided the voltage. It just happens to be connected to that minus terminal.
Okay.
Yeah. So if you bend that around, you've got that.
I have a question about this area. Is the VN directly connected to the plus without connecting to this line as well? Is there?
Yeah.
Oh, okay. Because I couldn't tell whether this was connected. So this is not a junction.
I did mention, I said that's not a junction, that's a loop. I've drawn it wrong. But that's, they're not connected because it doesn't work properly.
Okay. Thank you. Yeah, that makes a lot of sense.
Hello?
I was just wondering, when you said that we need to know if we can apply the virtual earth theorem, how do we know that, or do we get told?
Well, you just say, I'm assuming that the virtual earth system will apply because I'm not going to high frequencies or something like that.
Okay.
Just show me that you realise that there is something to think about here.
Okay. So if it's just like...
In an exam, I'm not going to worry as long as you say, I'm applying the virtual earth theorem because I believe it applies because I'm not going to high frequencies or something.
Okay.
Then I'll go, okay, that's fine. You know, you've understood it and said there's a problem here and I'm looking at the problem.
Okay.
That's all.
Thank you.
So that's linked to A, that's the amplification decreasing.
Yes.
Yeah.
Yeah. That's why there's a little capacitor inside the op amp. If you go back to the original side, that actually short circuits the gain stage at high frequencies. Because at high frequencies, the signal goes through that capacitor, goes around the gain stage, so the gain drops off. And it's deliberately done to maintain stability at high frequencies. Otherwise, it's all over the place.
That's what we did in T9.
Right. Well,
The graph that drops off.
yeah, the graph drops off. Yeah, exactly. You plotted that. And the big graph that you've got is the operating envelope of the op amp. When you apply feedback, you operate in that space. And then you've got a flat line of constant gain all the way across until it hits the descending line, and then it can't work anymore and it falls away. Runs into practical problems. And that's where virtual earth theorem doesn't apply anymore, once you've hit that line.
Thank you.
We're having a look at the second tutorial sheet in our PAT, and in the answers it said that the first one was a non-inverting and the second was a Schmidt, but we thought it was the other way around.
Yeah, I made a mistake.
Oh, okay.
Well, I made a mistake, corrected it, but then they never uploaded the corrected version.
okay.
It's out of my hands at that point.
Okay. That makes sense.
That's Thomas Andrich's problem.
Okay. No, that's fine.
But yeah, good.
Okay.
But it's made you think about it. So that's
Yeah. Okay, thank you.
I'm still not fully understanding virtual earth theorem. Is it just saying that the two, because of the feedback loop, that the two are the same?
Yep.
So when does it not apply?
when we have positive feedback, which is what we're looking at shortly.
Okay.
And if you have signals that go out, if you go outside the supply rail, for example, then you can't modulate the output anymore to match the input, and then just goes wrong.
So even if the plus terminal, if neither of those are connected to ground, what happens then?
Well, if neither of them they've got to be connected to something.
Yeah.
But it could be connected to a bunch of resistors or another voltage reference or something. All it does is it maintains the difference between these 2 points at zero. The difference between them is zero. What it's doing is that it sees a voltage here, and the op amp will adjust its output voltage up or down or whatever to affect this negative input, and it will adjust its output here to reduce the difference between these two to be as zero as it can, if it can possibly do it. If you get the connections around the wrong way, then it will adjust its output to try and minimise it, but the output's been connected wrong, so it'll just actually make it worse. That's positive feedback.
Right, yeah.
So it tries to minimise, tries to maintain the difference between these two as zero. That's all it can do.
Okay.
And they can do that within certain constraints, which is the output cannot go above the power supply rail. So if you're asking for more gain, you get clipping and stuff like that because it can't do it anymore. And it can only do it if the gain of this is very, very high. And the gain of this falls away with frequency. So when you get to a megahertz, for example, for a 741 op amp, it's all over, and it's not really an op amp anymore.
Okay, all right. So
A is then 1 rather than 100,000. And if you put 1 into those equations, you'll get the right answer, but it won't be very high.
okay, yeah. All right. So then, so when it applies, and then you just say V whatever equals, so that you make them
just say,
equal.
just say those two are equal,
Yeah.
and you work out what's the voltage of this one, wherefore the voltage of this one, and there's got to be some variable that you can adjust to make them equal.
Yeah.
Otherwise, you're in a rock and a hard place where you're over-constrained.
Okay. All right. Thank you.
Okay, so just to confirm, I know you said it, but the simple concept is that, of course, the virtual earth theorem, it's just the assumption, like the difference between this, and later in the, later in the subtractor, what we can just do is using that simple concept of KCL, that essentially, since we know that one of them is attached to ground, let's say the non-inverting, then the inverting is not, and we know at that point both of them are zero, then we just assume, like I said, how do I move these slides? What I was trying to ask is, Yeah, for example, we assume that if at one point both of these are 0, then that means that, for example, we assume that whatever is coming here, the current, and whatever is coming here has to be like, how to say, because of KCL result in this being 0 and this 0.
Yeah.
And we can just, like you said,
just say that.
yeah, simply use this.
0,
Yeah,
and then use that to work out what's going on here.
yeah. Or yeah, we could just simply treat this as two different sources, voltage sources, suppress them individually, and then just or even use other these. Yeah.
You do that to work out what is happening at V minus, what's the
minus,
expression of V
equation,
minus,
yeah.
and then you set it to be equal to whatever is at V plus.
Which is
And if
just
it's not
a
obvious
voltage
what's at V
divider.
plus, you have to get an expression for V plus as well. So here we've got an expression for V plus, which is potential divider, and here we've got an expression for V minus, which is two potential dividers.
Yeah, so, but what I meant to ask is that earlier, that essentially we can just apply the same basic laws you told us from the very start of the introduction, with the understanding that that an op-amp works, and that just ultimately I want to confirm, whenever we say that V in is ideally the input impedance for the op-amp is infinity, that's just a way of assuming that we assume that that none of that signal is wasted and all of it reaches the op-amp, right? And when we say that the Z out, the output impedance is 0, that's just our way of assuming that there are no loading defects, whatever, and it just perfectly gives the signal. Which of course is unrealistic.
Yeah, but it's pretty close.
Yeah, but we can assume that in some cases.
And in most cases, it's effectively true.
It's close enough.
It's close enough. Yeah.
Okay, thank you.
Sorry, it's not related to this lecture about the